I wanted to talk to you today about thousands, not billions, which is kind of a popular title for the results of the RATE project. And basically the bottom line of that project, we found very strong evidence that the world is young after all, which is a fantastic result. We weren't sure what we were going to find when we started this project. In fact, we were a little bit fearful when we started the project because we were committed to reporting the results as we found them. And a number of scientists, creationist scientists, had addressed this particular problem individually as a single scientist and had not been able to quite find the clue to be able to figure out what the problem was. And so when we started this work, we were fearful if we didn't find a good answer, we were going to embarrass ourselves as well as the Christian community as a whole. So we bathed this whole project in prayer and asked the Lord to really bless as we honored His word and tried to find out what the conflict was between thousands of years that the Bible talks about since creation and billions of years, as Carl Sagan used to say, for the conventional community. Now that's over a factor of 1 million difference between those two estimates of the age of the earth. So surely there ought to be some information in there to be able to give us some clues. But nobody had been able to quite sort it out. There's all kinds of evidence, geophysical evidence to say that the earth is young, but the basic problem was this issue of isotope dating. You may recall that nuclear decay was discovered about 100 years ago, and that became the predominant method of dating things, estimating as you had a radioactive element, which was the parent element, decaying into a daughter element, like uranium turning into lead. If you measured the amount of lead that was there and could estimate how much uranium was there to start with, you could get a fairly accurate estimate of the age of the earth. And it made sense if a number of assumptions were true. And I'm going to go through some of those assumptions, and it turns out one of those assumptions was seriously wrong, that we had thought was probably the strongest assumption, and we agreed with ourselves actually when we started the project. Well, let me tell you a little bit about who was involved in this project. There was a number of these, and you'll probably recognize most of these if you've been in the creationist area very long. I'll point to this one over here. This is me in the front. You recognize me here. To my left, the fuzzy-faced guy was Russ Humphreys. He's a physicist, and at the time of the start of this project, he worked at Sandia National Laboratories. To my right is John Baumgardner. He is a geophysicist dealing with the mantle of the Earth and primarily modeling the mantle of the Earth. He was at Los Alamos National Labs at the time we started this project. Both of those gentlemen, both Russ and John, about 4 years into the project, retired and then came to work full-time for ICR. Back over in the corner here is Gene Chafin. He is a physicist, was working at Bob Jones University. Behind him is Don DeYoung, an astronomer at Grace College in Winona Lake, Indiana. And your previous speaker, Steve Austin, a sedimentary geologist from University of Washington and Penn State University. Andrew Snelling, a hard rock geologist, currently works for AIG. At the start of that project, he worked for AIG and then came to work for ICR and is now back at AIG again. The difference between a hard rock geologist and a soft rock geologist is primarily soft rock geologists work with sedimentary rocks and hard rock geologists work with igneous rocks. So we had both specialties represented in the project, and we needed them. Behind Dr. Snelling was John Morris, the president of ICR, and he's probably responsible for the vision of being able to allow this project to proceed. He really encouraged us. Dr. Ken Cumming, head of the graduate school and the research program at that time. Bill Hosch, a geologist, a field person, did a lot of the field work and also did a lot of the laboratory work preparing the samples. And then, oh my goodness, my age is beginning to... Steve, you here? I'll have to... He's our Hebrew scholar from Master's College, and I'm just terribly sorry I forgot. Yeah, that would be good. Good idea. Where is it? Steve Boyd. Steve Boyd, there you go. Dr. Stephen Boyd, Hebrew scholar. I have this problem. When I talk about the Ice Age and I talk about the geological evidences for ice sheets and glaciers moving, there's always one slide that I show in my presentation which shows an erratic. And quite often I can't remember that name, erratic. And so I asked the audience to help me, and nobody knows what the word is. And finally, the best I've been able to come up with is a biblical term for a reprobate. Oh, well, what are you going to do? Anyway, those gentlemen were all involved in the RATE project. There was 8 of us that were the primary scientists. Actually, I didn't consider myself a scientist on the project. I was primarily the manager. Previously, I'd worked for the U.S. government and had run a 5-year field project in which I had under contract university types, government agencies, and private companies. And I drew all those people together into a field program on cloud seeding up in the Sierra Nevada between Sacramento and Reno. So I had a lot of training on how to do contracting and managing of programs like that. So that's how the Lord prepared me to be able to do that particular project. Well, I just need to refer quickly to a couple of books that are available, several resources. This is the primary book that those of you that are really highly technically trained or scientists or have friends who you want to give a very highly qualified book to, it's the final report to the project, Radioisotopes, and it's volume 2. And there's about 3 volumes in the back of the table there. Whoops, well, didn't show the other one. There's also a volume 1, which we wrote. And I need to tell you that the project was an 8-year-long project. It had 2 phases. The first phase went for 3 years, in which we got the group together and had to figure out what we were going to do, because none of us at that time knew how to approach the problem. So this was one of those things where iron sharpens iron. The men got together and we selected the experimental hypotheses, we did our literature searches, and we published volume 1, which was basically saying what we're going to do. And we had the hypotheses all spelled out. And then we did a 5-year experimental phase and reported the results of that in this particular project. So we actually had hypotheses set up that we published before we went and did the experimental work, and then reported on the results that we had. Now, I'll have some other materials at the end of the lecture here to show you. There's another book actually called Thousands, Not Billions, which is intended for a more general audience. So don't everybody go back there and buy that big, heavy book. It's for scientific use. Okay, now this project was really important, and if you struggle with this issue of the age of the Earth, these are some of the reasons that it is an issue. Evolution requires long periods of time, and the billions of years that typically come from radioisotope dating provide that time. But if in fact the Earth has not been around for billions of years, like the Bible says, then there's not time for even evolution. Even if you had lots of time, billions of years, we don't believe evolution would occur even then. But without time, it's impossible. And it would be very clear to anybody who looked at the problem. Now, the problem is that some Christians have accepted the idea of evolution, theistic evolution, progressive creation, and various other views. And that decays or degrades our reliability of Scripture. It begins to affect how confident we are in the Word of God, and it allows for more and more compromise. So the real bottom line to this question, this was really easy to specify what we were trying to do with this project, to answer the question, is the Earth really old? Well, there are 3 basic assumptions that are built that you have to rely on when you're doing radioisotope dating or even other kind of dating efforts. And these are, first, the initial concentration of the daughter element. You have to be able to know that, and quite often you assume it's 0. If you start with the parent element, like all uranium, and then you measure how much lead you have, which is the daughter element, then you can estimate how long it's taken for that to acquire that much lead. In fact, if I didn't have the Bible, or I didn't have any other independent reason to believe that the Earth is young, by simply taking that technique, I would assume that the Earth is old as well. But we have another source of information, which is coming from Scripture, and now we have to go back and check why are we coming up with that result. There's a second issue, and this turns out to be the most important one, is that we assume that there's a constant decay rate. That is, when you measure uranium turning into lead or various other isotopes like carbon-14 turning into nitrogen-14, we assume that that decay rate is always constant. I was taught that in school. Everybody on our research team was taught that. You probably are taught that when you went to school as well. And it's assumed that that's the case. In fact, most of the evidence would indicate that that's really true. And so we had assumed that we went into this project, that assumption was probably valid. It turns out that that's the one that was most wrong. And we were surprised at that. And thirdly, it has to be a closed system. That means that in the process of the parent element decaying into the daughter element, you don't lose or gain the parent or the daughter elements by any other process other than nuclear decay. It has to be closed, otherwise you can't count it as a way of doing the dating. Well, these were the basic rate hypotheses that we developed during the first 3 years of the project. We began to say there had to be some kind of a change in the decay rate. Now, when we started that first 3 years of the project, we didn't think about that. But as we began to do the literature search, we began to really get at the issue of a factor of 1 million or more in difference between the biblical age and the radioisotope ages. There had to be something else going on, and that implied that something had to change in the decay rate. So we assumed that there must have been some kind of a process by which the decay rate was accelerated at the time of sometime in creation or at the curse or during the flood. Those seem to be the three main places in Scripture that could probably happen. We also said that possibly some of the daughter elements may have been primordial. That is, that at the end of at the creation week, at the end of that time, there may have already been some daughter elements there. It didn't start from zero, but we had no way of knowing. It turns out that the project that we found could not explain all the material. It explained a lot of the daughter element. So we were able to find at the end of the project, yes, there had been accelerated decay, but there still needs to be some kind of a process back at creation. Now, that's a problem for some people. When you talk about decay, you automatically think that would conflict with what the Scripture said when God at the end of the week of creation said everything was good. How can something that is decay be good? Well, possibly that's a term problem. That is, it may well be we should be talking about transformation, we should be talking about a nuclear process, and the word decay is where the term comes in. I don't know, we haven't resolved that fully, but some of you may be more sensitive to that than others. We also said that the radioactive processes have produced evidence of accelerated decay. Now that was the key. We could hypothesize accelerated decay and get everything to work out fine, but unless you had some evidence that it was going on, then you're just blowing smoke. So we had to be able to find evidence for that. And fortunately, in the project, we found that evidence, which is exciting. Now, in the project, we did a number of things. And I'm talking about laboratory work. We took a lot of rock samples, particularly granites. Everything we dealt with had to do with granite. Well, I shouldn't say that. We had to deal with coal and diamonds as well. But granite was our primary rock that we were working with, trying to understand how to date that. And you'll see in a moment why we selected that. But we processed these rocks ourselves. We went out in the field and collected them and processed them, prepared them for laboratory work, but we did not do the actual laboratory work ourselves. We sent these off to professional laboratories. Now, the reason for that is twofold. First of all, we needed about 6 or 8 different types of laboratory results. And each one of these laboratories, if we set up our own laboratory, we're talking maybe $100,000 to set up one laboratory with the equipment. You had to get a technician. You had to run the laboratory for several years to be able to get a consistent result so that you could believe the results that you have. And we decided that that was too expensive if we had to do that for 6 or 8 different type of processes. But the second reason is probably even more important, and that is if we did the laboratory work ourselves, nobody would believe the result. So we decided to send the samples off to professional laboratories, have them do the analysis, send the results back, and then we would interpret those results in terms of the process we were trying to explain. Here's an example of some of the work we had to do. We take a chunk of granite, just plain old granite, break it up, separate the crystals out, and pull out what are called zircons, which is a small crystal inside. And you had to separate those either by separating with tweezers under a microscope or sifting them through sieves, or in some cases put them in heavy metal liquids, separate off lower density from heavier density in those materials. So there was all kinds of complex laboratory techniques we had to do to prepare the samples to go to the other labs. Here's some examples of some of the sieves we used, and that's a pestle and mortar made out of iron, which is different than a pharmacist would use. It's a little heavier. In fact, you use a sledgehammer with it. So it's heavy work. Here's some of the samples that you get. You filter it through and put it in various heavy liquids in order to separate them out. Okay, I'm going to report to you basically 4 experimental results. And there's a number of other things that we did. For example, Dr. Stephen Boyd did an incredible study on Scripture to be able to show that Genesis 1 through 11 should be taken literally. It should not be taken allegorically, which is the basis of why we believe Scripture is an independent source of information to approach this project. But I don't have time to go into that. I'm not a theologian, so I don't have all the expertise to explain it. Most of you are more scientifically oriented anyway, so I decided to restrict this to 4 scientific results. The first one is the helium diffusion results that we worked with, and Dr. Russell Humphreys was the primary scientist responsible for this. Basically, here's the bottom line, the result of his experimental work, and that is that he found that 1.5 billion years of nuclear decay occurred between 4,000 and 8,000 years ago. And actually, in a way to say that more scientifically, he found that the age of the Earth, based on his helium diffusion results, was 6,000 plus or minus 2,000 years. We not only got a good estimate for it, and it was relatively short, in agreement with Scripture, but we had an error bar on it, which is really outstanding. Okay, here's how we approached this, or he did. We took a sample of granite from various depths down in a core that was drilled by the Los Alamos National Laboratory in New Mexico, associated with trying to do a thermal heat experiment. In other words, they were trying to tap hot rocks in steam to produce power by power generators from the geophysical heat. In these granite samples, which we had a core that went down 12,000 feet, we were able to take those those granite cores and separate out little crystals called zircons. Now, zircons is a material of zirconium silicate. It's actually, some of you ladies actually have some of those on your earrings probably. They look like diamonds, but they're much cheaper. And so anyway, those little rocks that you have on your ears are the kind of crystals that we were using for this study. Now, the reason they're so essential to this project, they were like little parcels or samples of uranium and lead. And each one of these little zircons, which are very, very small, in fact, here I'll show you, here's a regular microscope view of what zircons look like. And you can see that the scale there in the diagram, the 100 microns. 100 microns is about the size of the diameter of a hair on your head. So they're relatively small, but you can see them under on a regular light microscope, or you can look at them in more detail under a electron microscope. This is similar type zircons. And the reason they're important is because within the zircon, they have uranium and lead. It's like a little parcel, and it's enclosed so that the uranium and the lead can't escape. And as the uranium decays into lead, it's all held inside of that particular parcel. These parcels can go through all kinds of geophysical processes. For example, actually go through a volcano and come out the top without being melted because they have such a high melting temperature. So it's like a little parcel that can go through a lot of process and still give you the information on the age of that particular zircon. These zircons, I should say, the uranium in the zircon, typically uranium-238, will decay to lead-206, 207, some of those. And it goes through, in the decay chain, several processes by which alpha particles are released and forms helium. An alpha particle is nothing more than the core of a helium atom. So when the alpha particle gets done flying out in all directions, it grabs onto some electrons and becomes helium. So within the zircon and in the surrounding granite, you have helium that's being produced in addition to the lead. So Dr. Humphreys got the idea, possibly we have an alternative dating technique for these zircons, or the granites themselves, by looking at how much helium is still in the rock and how fast it's diffusing out, instead of just looking at the lead that's there. Now here's an example of a uranium atom with a bunch of electrons around it and throwing out alpha particles. An alpha particle is made up of 2 protons and 2 neutrons. They fly out in all kinds of directions, and they produce damage in the rocks around it, particularly the biotite. Granite's made up of the white rock and the little black specks in it. The black specks is the biotite. It's a mica that can be formed off in layers, and embedded in that mica are these zircons. And when the zircons throw out the alpha particles, they leave trails of damage in the surrounding mica. Well, we'll get back to that more in just a moment. Here's the core sample that we had from Los Alamos, and you can see from this diagram here, we had measurements initially before we started the project of 5 different samples at different depths, all the way from almost 1,000 meters, about 3,000 feet, all the way down to almost 4,000 meters, or about 12,000 feet. And we had the measurement of temperature at each of those. Up near the surface, 3,000 feet below the surface, the temperature was just above the boiling point of water. That's why they were looking there, was to be able to find the heat to generate steam. And as you go down, the temperature gets hotter. It's almost 300 degrees down at the bottom. And in looking at how much helium was still in the zircons in that sample of granite, we found that the sample that was at the coolest up near the top still had 58% of the helium that it should have had if 1.5 billion years of uranium had decayed into lead. In other words, the helium was being trapped in that zircon. It was not escaping. It was slow to get out. But as you might expect, if the temperature is higher, you're going to get more of it out of there. And in fact, down at the very lowest levels, where the temperature was almost 300 degrees, there was only 1/10% of the helium still there. And so it's a very exponential type process. Well, this is a typical example, and this allowed us the opportunity to estimate how fast helium was diffusing out of granites as a function of temperature. And it's similar to the process where you take your child or your grandchild to the carnival and you buy them a helium balloon, and the helium escapes out through the rubber, and overnight the helium will kind of settle down on the floor because it doesn't have enough helium in it to hold it up. The same thing goes on in granite, except it's much, much slower. And the rate at which the helium escapes out of the zircons, out of the biotite, and out of the granite can be measured in terms of diffusivity. So we've got plotted on the left side here diffusivity in the units of centimeters squared per second, which I'm not going to try to defend that. But on the horizontal axis, the temperature in degrees centigrade. Now the hottest temperature is to the left. Diffusivity is a measure of how fast the helium escapes out of the rock. So therefore, at the hotter temperatures, it should be higher. Now, originally, we had this data here. And actually, we had to then put that data into a model of a zircon, a 3-dimensional model that would allow the helium to diffuse outward, and from that, calculate what the diffusivity is. We had 2 models before, at the end of the first 3 years of the project. One based on a uniformitarian model, which estimated it took 1.5 billion years for that helium to escape, and this gave the plot of what the diffusivity would be for a uniformitarian model. We then plotted that same data in the red dots up here for a creation model, assuming that was 6,000 years. That means that if it's only 6,000 years, the diffusivity would have had to been a lot faster. And the difference between these two is about 5 orders of magnitude in diffusivity here. You notice these are 10 to the minus 23, 21, so on. There's a factor of 100 here between each one of those major blocks there. So there's about a factor of 100,000 difference between these two, but we didn't know what the result was going to be. We predicted that the creation model, if we took the granite samples, the zircon samples from the granite, sent it to a laboratory and had them actually measure the real diffusivity, it should match this curve up here if the creation model is true. It should match this curve down here if the uniformitarian model is true. Now, there's quite an interesting story about getting this done. We actually had this work done at Caltech, and we had to kind of do it through a third party because we knew that if we submitted it directly under Institute for Creation Research name, they would probably refuse to do it. Now, that's not underhanded subterfuge. That's typically done by many mining companies when they want some analysis done because they don't want people to know where the sample came from or who they were so that they don't lose the investment they have in their program where somebody goes and then buys the mine or something like that. So we had that done, and the results were absolutely incredible. This was in the 5-year phase of the project. It took about 2 years to get this sample processed, and the data is in blue from the samples that we had, and when you plot it up there, it just extended exactly what the creation model did. Dr. Humphreys said he had never in his whole career had data come out so close to a prediction that he had ever made before. I mean, it was just incredible. Well, what this did was give us an alternative clock for estimating the age of the Earth. Now, I've tried to illustrate this here with 2 sundials. On the left is a sundial indicating the decay of uranium into lead in the bottom of the sundial. And over here is helium diffusing out of the rock. You got a bunch of helium here in the rock diffusing out of the rock away from the deal. Originally now we're going to have the sundial on the left have accelerated decay. At some time in the past, God turned the lever, kind of a simplified view of how God operates, but he turned the lever so that the process of decay from uranium to lead was accelerated. It was going on at a much faster rate than we have today, on the order of 1 million times faster. During the development of lead in the zircon accumulated, helium was flowing over into our other sundial and was escaping out of the biotite. The difference is that the helium escape is a chemical process, and the uranium decay is a nuclear process. And it appears that during this, the diffusion of helium out of the zircons was not affected by the uranium, the accelerated decay over here. So that meant that this clock was going relatively slowly, while this one was going very, very fast while it was accelerated. And then at the end of that process, God closed the valve off and it came back to the rate that we measure today, and the helium continued to go at the same rate. When you do the timing on that, you can't see this very well with the light here, but this comes out to 6,000 years, plus or minus 2,000 years, and this came out to 1.5 billion years. So in other words, what we have here is an alternative to the standard uranium lead. If you have an accelerated process by which the decay has sped up, you're going to have a much longer estimate for time. Whereas if you have a process that's not affected by the decay, it would give you a true age, which is what we believe the helium was doing. Well, that was an incredible result of the project, but that was only one of 4 major results. The second one here now gives us some direct evidence of an accelerated decay. First of all, the helium that's actually still in the rocks is a direct evidence itself, because if in fact the Earth is 1.5 billion years old and the diffusivity is what we measure today, that helium shouldn't be there. There shouldn't be any helium left in the granite at all, but it's still there. So here you've got kind of a total estimate of what's going on with accelerated decay. Well, we needed something a little bit more evident, and that is from the radio halo studies. It turns out that granite, when you have these little zircons with uranium in them throwing out alpha particles, the alpha particles thrown out in all directions produce damage deposits in the mica and the surrounding rock. So we started to collect granite samples from all over the world to be able to look for radio halos. Radio halos, I'll show you a diagram of one in a moment, but it's a kind of a little, well, I'll wait to show you. I went with Andrew Snelling, for example, to one place to get some granite. If you've ever been to Yosemite, you know Yosemite is a beautiful place to find granite. You get up there and the whole park practically is filled with granite. So I felt that we had to get some samples there. So he went with me to Yosemite about 2 years into the second phase of the project. And we decided to hike from Glacier Point down to the valley floor, collecting samples along the way. Now I have to warn you, never be a geological assistant because you get to carry the rocks. And I had a day pack with me. Dr. Snelling was a geologist, so you notice he doesn't have a pack on. But he has a GPS, so as we went down the trail, he would figure out exactly where we were, and he had his hammer with him to knock off the rocks. Oh, and I need to tell you, you can't just do this yourself. You can't go out and collect rocks in a national park. You have to have special permission. You have to write a proposal, a research proposal, which we did to the park, and they agreed to that, and then we had to write them a report at the end of the project. But in addition to that, getting permission, they required us to kind of hide from the public. They didn't want people seeing us knocking rocks off the trail. So I would be the lookout. I'd stand on the trail and I'd look up and down the trail and I'd tell Andrew, okay, go for it. And he'd be kind of behind the rock and he'd take his hammer and knock off a fist-sized chunk. And he'd put it in a plastic bag and label it with its location, all the stuff about the rock, and then put it in my pack. By the time I got down at the bottom of the Glacier Point Trail, it's called the 4-mile trail, felt like 6 or 8. By the time I was down there, I had 40 pounds of rocks in my backpack. My wife, who's in the back of the audience here, she and Mrs. Snelling picked me up at the bottom of the trail, and I was about done in. It's all I could do to get in the car. At any rate, that's one of the places we collect rocks, granite samples. We did also in Southern California, east of San Diego. We did in the White Mountains in New Hampshire. We had samples from Sweden. We had samples from Australia. Over 20,000 samples, not hand rock samples, but radio halos within the various samples that we got were processed in this effort. Here's what we were looking for. These are called radio halos. At the center of this so-called radio halo is a zircon, which is full of uranium or some other radioactive material. When it throws out the alpha particles, it damages the surrounding crystal structure and leaves it with this kind of a concentric sphere around the center of it. But because this occurs in mica, which is layered, you can actually peel off the layers of the mica with a piece of Scotch tape and put it on a microscope slide and look under a microscope and find these particular radio halos. The different radio materials, whether it's uranium or polonium or thorium or various radio halos, will have different numbers of rings and different size. So it's kind of like a fingerprint. You can tell what kind of radio halo you have by how big it is and how many rings it has. Well, here's an example of a zircon throwing out alpha particles in all directions buried in the black mica, and it produces this what are called halos. It's actually spherical, but in 2 dimensions, it's just a series of circles. So therefore, they're called halos. And this then, here's your granite sample. We're going to kind of home in on the black biotite. And then we're going to go inside the black biotite and show the halos being formed. And most granite then has water flowing through it, hydrothermal fluid, that takes off some of the decay products that are produced by the uranium. And one of the most important ones is polonium radio halos. Polonium, as it comes, it actually flows in the water and forms centers downflow from the uranium center. At any rate, these polonium radio halos, we were able to locate these, and typically they're smaller. They don't have as many rings. And there's various isotopes of these, and so you can have different polonium radio halos. The importance of these is that they have a very short half-life. These polonium halos sometimes are on milliseconds. In other words, half the polonium will decay in less than a millisecond. Some are more on the order of a week or days, and the longest one's on the order of a month. That means that the polonium radio halos had to have formed in a very short period of time. In a matter of weeks or months. And that's important because they will only form in solid material. If you're in magma, which is hot, if this granite is molten still, the radio halos won't form. And if it's in fact hotter than about 500 degrees centigrade, they won't form because the radiohalos will disperse and the rock, the crystal structure will reform. So the rock had to be colder than about 500 degrees centigrade. Now that tells you that the granite itself in this process, whatever was going on when we had this accelerated decay, had to have cooled very rapidly. That tells you it was a very sudden, very quick process. Not only the granite, but the radiohalos themselves had to form that way. So we have now a direct estimate that the rock had to have been formed very, very quickly, and the accelerated decay had to be very fast because those radiohalos take up to 1 million alpha particles being shot out to produce the radiohalo itself. So that meant that the accelerated decay had to have happened very rapidly as well. So we had direct evidence then from this that we had accelerated decay going on sometime back in history. From all the thousands of samples that we took, we then plotted the frequency of radiohalos as a function of the conventional time from uranium-lead dating in these granites. And we found a peak of their occurrence in the conventional time frame back a little earlier than about 500 million years ago. In other words, the estimate for these granites is on the order of 3 billion years. That's about a half a billion years. From the conventional time frame, you have a lot of those occurring at a particular time. So this was an instantaneous process that happened in the past. Now, those dates obviously are not, we don't believe are true biblically, but that tells you from the conventional time frame what happened. Well, that was a very important result. Another one, which is a little bit easier to grasp, that's the hardest one to grasp, is some work that both Dr. Austin and Dr. Snelling did on isochron discordance. If you look at different types of radioisotopes that are decaying, and you collect samples in Grand Canyon, you've probably seen this diagram from Dr. Austin's talks in various times in the past, cross-section of Grand Canyon. We had to collect samples of igneous type rocks that squeeze up between the formations and layers in Grand Canyon. Here's a looking down on Grand Canyon, kind of a horizontal path. This is the Colorado River coming down from Lee's Ferry, turning and going through the park. In various places, you can get to igneous basalts, the Cardenas basalt, the Hance Rapids sill, Bright Angel sill, Bass Rapids sill. All these various things are magma that came up we could collect samples on in order to be able to look at the ages. And here's some of the fun part of doing this research is getting to go down in Grand Canyon. A number of you have been on our raft trips, and you may recall that we were collecting rocks during part of that to take out on the raft, and the raft company that would then ship it back. So I didn't have to carry it. That's a great way to go. You just bring them down and throw them in the raft. We had groups that went with us. These are the kind of formations that you had, and we took various samples. We know exactly where they were taken. Now, here's a very interesting result that came out of all these. This is a plot of isochron age. Now, I need to just say briefly, you can estimate the age of rocks from radioactive decay using an isochron diagram. And the slope of the plot of the various isotopes gives you an estimate of the age. That's called isochron age. We could do this for various types of isotopes. We did this for potassium argon, which has an atomic mass of around 40, rubidium strontium, where rubidium's around 90, samarium neodymium, where it's about 150, and uranium, which is about 238. That's the atomic weight in atomic mass units. We then plotted the estimated age of that rock from the conventional estimates, and here you see the different kinds. We got Elves Chasm granodiorite, and some amphibolites, Bass Rapids diabase, and Cardenas basalt, all these from Grand Canyon, different colors, and with their error bars. Interestingly enough, when you have these two, the samarium neodymium and uranium lead, that particular type of decay is called the alpha decay, like we've already been talking about, and it produced some of the oldest ages. They're estimated here on the order of 2 billion years or a little less. The other type is beta decay, which is a different kind of decay, and it gives younger ages. But if you plot this on a diagram as a function of atomic weight, you notice there's a kind of a trend. Now, if you look at carbon-14, it's going to be way down here somewhere. We don't have that actual data on this diagram, but we don't know what causes that, but we think that maybe in the future we will understand that. So we published that in order for people to get prompted to look at more research in that area. But the importance of this whole thing is that there is a major discordance between the different types of isochron ages depending upon the element. Here we got samples from different places. Outside the error bars, they don't agree. And they don't agree between different types. I mean, all of these rocks should be about the same age, and they're not. So there's a major conflict simply in trying to estimate the age of rock with the different isotope techniques. That alone says there's something wrong with the conventional technique. Okay, then carbon-14. This is a really interesting one. We weren't going to do this particular effort when we started the project because we wanted to deal with long-age isotopes. Carbon-14 only has a half-life of 5,700 years. But a friend of ours told us that this information had been published in the literature, and we didn't even know about it. And so Dr. John Baumgartner decided to take this on, and he found an incredible result. Carbon-14 is used for dating such things as bones and trees and coal. Now, coal is thought to be 100 or 200 million years old, and there should be no carbon-14 in coal. But that's what had been found. There was a new instrument that had been developed about 20 years ago now called an atomic mass spectrometer for trying to measure carbon-14. And the conventional scientists had been finding carbon-14 in coal. It shouldn't be there if it's 100 or 200 million years old. So they published this over and over and again, trying to find out where the error was. And there was something like 70 different reports in the literature of carbon-14 in coal. Well, when we found out about this, we decided we got to investigate this. So we, come back here. We had some samples done. Steve Austin got some samples from the Pennsylvania State Coal Lab. We processed them to confirm that these reports that were in the literature, we could duplicate it. In fact, we found it. The idea behind carbon-14 is that there is carbon-12 and there's carbon-14 in the atmosphere. The carbon-14 is produced by cosmic particles striking nitrogen-14 and producing it in the atmosphere. The carbon-14 is a very, very small percentage of the total carbon in the atmosphere. But the ratio between the two is maintained in the atmosphere and in plants and animals. As the plants take on air that has a particular ratio of carbon-14 to carbon-12 in it, they take on the same ratio. As the animals eat the plants, they take on the same ratio until they die. Then when the animal dies, the carbon-14 then begins to decay, and you can estimate the age at which the animal or plant died. So that's the whole technique behind it. What would happen if this had happened during the flood? Well, here's the atmosphere with its carbon-14, carbon-12 ratio. It's in the trees and the plants. Suddenly the flood comes along and it buries everything, all the plants and animals. And what kind of an age would you expect to find if that only happened 4,000, 5,000, 6,000 years ago? I think about 4,500 years ago. The coal and the other plants and materials in there would lose the carbon-14 and turn into nitrogen-14, and the ages should be much younger than the conventional view would be. And so that's what we, in fact, began to check. This is the results of the conventional reports. Basically, it's expressed in the percent modern carbon, which I'm running out of time, so I won't go into detail. But basically, that was the average for the 70 samples that had been published. This is the average for the 10 samples that we did. The other one was 0.29, this one's 0.25 essentially. So we were able to confirm that the data that the conventional reports are done were true. But let me stop that. I need to go back and make a comment here first. The problem with looking at coal, however, is there's the possibility that it could be contaminated. In fact, that's the big response that the conventional community says, that coal is obviously contaminated, either by doing the analysis in the laboratory or out in the field. It was contaminated in some way. And we would have to say there is a possibility of that. It's not too likely if you're very careful, but because of rain and so on dripping down through the formations into the coal, it's possible you could bring some carbon-14 down from the atmosphere. Well, Dr. Baumgartner had an idea. He said, let's look at some other kind of a carbon material. Let's look at diamonds. Diamonds are made up of carbon. Do they have any carbon-14 in them? Now, here's a perfect example of where the conventional community would never even bother to look at or ask that question. But we have. So we said, let's look and see if it's in diamond. The beautiful thing about diamond is it's so hard, it's the hardest substance known to man, the carbon-14 could not be contaminated if it's there. The question is there any carbon-14 in diamond? Well, we did that experiment, and guess what? We found almost as much carbon-14 in diamonds as there is in coal. And you can't explain it. In fact, the diamonds are 1.5 billion years old. They cannot be affected by environmental conditions. And yet, there's carbon-14 in them. If, in fact, we found that the diamonds and the coal could be estimated to be on the order of about 50,000 years old, but that's assuming conventional baselines. If you, in fact, assume that the flood had an additional effect upon burying a lot of the carbon material and sequestering a lot of the carbon-12 in the atmosphere, it would have changed that ratio dramatically between before the flood and after, reducing that 50,000 years down by a factor of about 100 to 5,000 years, which is about the order we think that the flood occurred. Not only that, but the various coal layers that we looked at, all these various ones should have been oldest near the bottom. They basically had the same estimated age through that whole depth, which we believe would have happened if it was caused by the flood. Well, that's a quick study of this project, but basically the bottom line is it's a young world after all.
I take it then that when you look at a polonium halo, that isn't from one alpha particle. There's
a million of them or more. It takes at least 1 million for you to be able to even see the radio halo.
Oh, okay. Yeah. Thank you.
That's right. It's a big number. And they had to happen fast.
I was told that you also do glacier type geology.
Ice Age work, yeah.
Okay. I, several years ago, purchased a book called The Iceman. Did they arrive at his age through carbon dating?
I don't recall the details now. It's been a while since I read that book, but they would use conventional techniques, yes. Yeah, that's right.
So that would be...
You'd have to adjust it dramatically downward.
I see.
Yeah, I don't remember what the age was. They probably, I would guess they estimated it around 15 or 20,000 years ago. So if you estimated it down by a factor of 5, you're in the ballpark of right after the flood during the Ice Age, in our time frame. The conventional view of the Ice Age is the last one occurred, the maximum of it occurred about 18,000 years ago. I believe it happened about 4,000 years ago. Yeah.
Good question, Larry. On the helium diffusion experiment, it seems to me that secular scientists could repeat that experiment fairly easily. Have they done so, and what results have they found?
This is really fascinating. About 3 years into that 5-year phase, we were beginning to get the results that I've reported to you here, and we just kind of cleaned things up for the final report after that. But we had enough information that we were able to submit a presentation to the American Geophysical Union meeting in San Francisco in 2003. And we were given the opportunity to present 3 poster sessions, one on the helium diffusion, one on the polonium halos, and one on the carbon-14. And at that conference, which is in San Francisco, there was about 12,000 geophysicists there, many of which specialize or run laboratories that do this kind of work. And they came by our presentation. We spoke with about 400 of them during an 8-hour day at our session, or at our presentation. And many of them would walk by and look at that, and they wouldn't want to talk to us. But many of them did, and they'd come up and they were just astounded. The basic conclusion was, this is real science. You guys need to keep really doing this, and I don't understand, I can't explain the results that you got, but it's really fascinating. And I'm going to go back to my lab and repeat those experiments. And a number of them did, and they confirmed exactly what we had found. So they're still scratching their head on that. We haven't seen all the results of that yet, but I think it's going to filter through the whole community. I might also say one other thing. One of our biggest critics, I've forgotten his name now, but he wrote a very important book on the age of the Earth. He basically reports to the American Association for the Advancement of Science on activities of creation researchers each year. And a year not long after we reported some of these results, he basically said, if those guys are correct, talking about us creationists, then they deserve the Nobel Prize. But obviously they can't be right because they're creationists. Good logic, right?
Seeing no other hands, a follow-up question to that. What would be the old Earth folks' response to those findings?
We haven't had a strong response to that. In fact, for a long time, it was real dead silence. But basically, the response that we have had is primarily online, although there was one publication by one organization, I forget now, in which they basically criticize everything we did as being illegitimate, that the techniques were flawed, and that we've interpreted it wrong, and all that sort of thing. We've responded, particularly Dr. Humphreys responded in great detail to many of these criticisms, and we just go around and around. We never get to the bottom of it, so we finally just kind of gave up trying to talk with them. But they're not about to accept it. It's quite often that the old Earth creationists are more upset by these kind of results than the non-Christian community.